All right, good afternoon, everyone. My name is Dulaney. I'm a student here at Minoris of Toledo. I'll be a junior this fall, and my mentors for this project were Dr. Noel Richardson and Dr. John Dorfman. And this project, I am searching for the elusive companion to the star Beta CMI. Beta CMI is a BE star, and as we just went over with Perchia, it's a star that's more massive than our own sun. It's brighter and hotter as well. And it rotates very rapidly, and sometimes those rotations can cause a decretion disk to form, and that's essentially just a gaseous disk that forms around the equator and orbits around the star. Here's an Irish rendition of what that would look like. This is the BE star 5 You can see the star is right there, and the pinkish thing around it is the decretion disk. And in the case of 5 you can see there's another star here down in the lower corner, which is orbiting the star 5 and that's the binary companion. And that's actually the purpose of this study, was to study the disk of Beta CMI to try and determine if there was a binary star there, as there was in the case of 5 It's helpful not only for the discovery of the star, but also because it helps us to understand disk evolution better and helps us understand the mass loss process for these BE stars a little better. Beta CMI in particular was a good candidate for this research because the disk has shown to be extremely stable through time. We have about 15 years worth of spectra here at Ritter, and it's been extremely stable throughout that spectra. There's also plenty of other spectra at other locations, and it's shown to be stable for decades. So it's easy to look at, and because it's not really changing much, so it's easy to study, which is actually really good because sometimes the disks can change a lot. They can vary a lot in their shape and size, or sometimes they can disappear altogether and reappear later, but for Beta CMI it's very stable. And it's also good because the disk is shown to be truncated, and that just means that the disk sort of extends outward from the star, but there comes a point where it could keep going, but something kind of cuts it off, or at least makes it less dense and kind of depletes how far it extends. And in the case of 5 that's because of the binary star, because if the disk were to extend out further, it would start to lose mass to the binary, so that kind of prevents the disk from extending out much further. And so we were wondering if that would be the case for Beta CMI, because past research has shown that it is truncated. And for this research, we've been using mostly Ritter data taken from the spectrographs here, also a little bit of NASA IRTF data, which is infrared data. And so we knew the disk was truncated, so the first part of the project we wanted to find this supposed binary. And if you imagine Beta CMI in space and assume that there's a binary orbiting around it, you can see Beta CMI would be here, and it's obviously acting gravitationally on the binary star, causing it to revolve around it. However, the binary is also acting gravitationally on Beta CMI, causing it to move around a little bit as well. And whenever we're looking at something that's emitting light in space, if it's moving, that can show up in the spectrum, because if it's moving away from us, the light that's being emitted will shift to the red end of the spectrum, and if it's moving towards us, that's going to shift to the blue end. And as Beta CMI moves around because of the binary, the disk is going to move around as well, following it, kind of sloshing around behind it. And so when we look at the emission of the disks, what we find is that the light being emitted is shifted to the red and blue ends of the spectrum as it's moving. So we know that it's moving, and we know that that must be because it's a binary that's causing it to move. So by looking at the emissions from the disk, we're able to prove that there is a binary star in orbit. And now that we know it's there, we want to learn more about it. And we start by looking at the orbit. And you can see here there's a few outliers in this, and the amplitude's kind of low, but in general it follows this curve pretty well, showing that there is orbit. This is showing the rate of velocity of the disk as we look at its emissions. And from rate of velocity, we're able to calculate period for the orbit of the star. And we calculated period a few different times, and the numbers were never the same, but they were always pretty similar. So we got a range for the orbit of about 165, between that and 190 days. This is showing the orbit that we calculated. You essentially apply a Fourier transform to the data, and that allows you to calculate the period. And this one is about 185, 190 days. It's somewhere in that range. You could revise the orbit to get something more exact by using data that has better signal to noise. Ours is pretty good, but it wasn't perfect, so we only got a range. Or you could also look at the absorption lines, because we looked mostly at the emissions from the disk. And after period, we want to know if the companion star is interacting with the disk in any way, because a lot of times it does. The companion star can heat up part of the disk and create a hot spot, or it can interact gravitationally and cause some regions to be denser than others. And so we wanted to know if there was some sort of a density structure, some kind of density wave within the disk. And we do that, again, by looking at the shifting in light to the different ends of the spectrum based on its movement. Because if you imagine the disk orbiting the star in space, from our perspective on Earth, part of it will be moving away from us as it orbits, and part of it will be moving towards us. And that movement, of course, would show up as red and blue shifting in the light. And we can see that on this graph. There's the black line with the double peaks represents the emissions from the disk, and the red line represents the emissions from the star, beta CMI. And one peak represents the red side of the shifting, one peak represents the blue side of the shifting. And so if it's got uniform density all across the disk and we track the motions, then the ratio of violet light to red light is going to be the same, very consistent. However, if there's some sort of a density structure within the wave where one side has more mass than the other because the binary is acting on it, then the ratio of violet light to red light is going to be thrown off a little bit. And when we look at that ratio, we find not very much. We were expecting there to be a density wave, but there really wasn't much. This is kind of showing it doesn't follow much of a trend. So there were hints of some structure within the disk, but there wasn't much at all, so we couldn't really link it to the binary. If there is, yes?
What's the difference between the filled and the open circles?
The filled are spectra we've taken at Ritter, and the open circles are amateur data which we used to try and get VR measurements. So we kind of compared them, and neither one really tells us that there's much of a structure there. If there is a structure, it's small, and we can't say for sure that it's caused by the binary. So that was a little disappointing, but what we can say for sure about the disk is that we know it's truncated, and we know that there's a binary causing that. There are hints of structure, but they're weak, and we can't link it to the binary. It does raise some interesting questions, though, because if there is a structure within the disk, we could hopefully learn more about it by comparing it to the disks of other BE stars that are in binary systems and try and draw conclusions that way. Also, we were expecting there to be structure, so now we kind of have to address that in our models for beta CMI. Also, other questions, we've proven that the binary is there, but it hasn't been directly seen yet, so that could be done as well. And as I said, the orbit we have arranged, but it could be revised to get something specific. So the results and conclusions from the project, as I said, the disk is truncated. We have a general range for the period of the orbit, and there are hints of density waves, but nothing conclusive. However, it was a very successful project. We did get some great results, and we're going to be publishing a paper soon with our results, and we're working on that. And lastly, just want to give some thanks first to the NSF for funding the project, and also University of Toledo for giving me the chance to do this project. And then my advisors, Noel and John, who were both very helpful throughout the whole thing and really helped me learn a lot. Thank you. Yes.
Could you show this first radial velocity curve? Yeah.
This?
Oh, no. That
yes.
What are these error bars? What is the basis for assigning these errors? I mean, as far as I can see, most of them can't mean anything.
Well, most of the errors were pretty small, so it was low amplitude, but we generally got the errors to be pretty small, so it was kind of showing that our curve was pretty accurate.
No. I mean, I can focus on any one of these points that are not anywhere near the curve. They have an error bar. So what does this error bar signify? Is this some uncertainty that the real value falls within a certain interval of certainty, or what does it mean? I see that many of these points, or most of these points, are, if this is a standard deviation, say, in some distribution of measurements, most of these points are following many standard deviations off that curve. And so that's why I'm asking, what are these error bars? What do they mean?
Well, Error bars, we
How do you
weighted them.
determine that?
We kind of weighted them to be outliers as, like, I guess, less, I don't know.
They're weighted on the signal to noise and
Yeah.
the ability to measure the line from a cross-correlation function that was used on the edges of the disk. In reality, the absorption lines that are present in Ritter are just not usable for radial velocity measurements because they're too weak and broadened by the rapid rotation. And so the only thing that was left in all of our data to really measure was the H-alpha emission. And so there is, you know, tiny hints of little bits of structure, not much, but, you know, if there is a little bit sloshing around in the star, it's possible to think that, you know, these errors are maybe a little underestimated. But I think, you know, as a first look at seriously looking for a companion for this star, it's reasonable to say, you know, you can throw out 4 or 5 of those and everything kind of follows the trend of the sine wave.
So the disk is not a rigid structure. So it doesn't, of course, perfectly track the star.
So these are actually from
the emission
from the
line.
emission. So that's already very important, so that it's not the star actually.
Yeah,
No,
it's
the emissions of the disk.
the cross-correlation functions that we use were for the fastest moving gas in the disk. And so in a Keplerian gaseous disk, that should be the gas that is closest to the star that we're sampling as we measure the radial velocity. So hopefully it is a more realistic orbit. It certainly has worked for other BE stars in the past. I've done it for several for Gamma Cats and Tau. I've also seen it done for several now that they found, you know, companion stars that are hot ultraviolet stars, and they're seen in the UV, and the orbits all seem to match up. So I think that there's a companion there. I think we need better data to really pin down the orbit, but it's going to take some time and probably a couple telescope proposals to get it.
What about putting a running average to the data?
Then you'll lose the signal. I mean, that's, I mean, the signal is here, the amplitude's 2.5, 3 kilometers. You put a running average through stuff that varies by a few, you know, 5 kilometers or so, you're not really you're gonna kill the signal, I think. At least that's my impression.
I mean, you know, I have the same concern that if those are 1 sigma, you know, more than 2/3 of the points are away from that fit.
Yeah, but there's intrinsic variation in the disk. Think of this as being 2 statistically independent processes, one of which is the orbital variation due to the reflex motion of the star, plus another statistical process happening in the disk that's changing the structure, the densities within the disk. And that's producing a much larger variation, right? And so that's the reason that the spread here is a lot bigger than the size of the error bars.
I mean, I think the best thing about this is that it gives us the basis to go and ask for very high resolution blue spectroscopy that we can't do next door. And if we do that and we follow it up for a year or 2, we should be able to then get a nice orbit of it. But we need to get the photospheric lines. We just don't have them available in Ritter. It's a late type B star. Our spectrograph is mostly visible in or mostly looks in the red. We have, I think, 3 or 4 possible photospheric absorptions, but most of them are extremely weak, extremely broad. And if we really want to do it properly, we need to look at it in the blue and get lots of blue data to get the velocities. And we just don't have that yet. But we need to prove that it will yield something if we're going to get time order.
So these are emission, and I
Yes.
think you've just answered more or less my question about the absorption rates, but it seems to me you could choose a region of the spectrum that contains many absorption rates, and then use a cross-correlation of all the absorption lines, which should all be moving in the same speed and direction. instead of just one absorption.
Only if we go to the blue part of the spectrum
Only
of
if
the
you
mean
go to the
star.
blue?
which we struggle with everywhere.
Yeah, I mean, the throughput on the spectrograph, everything could be a shell. When you go into the blue, there's just very, very little signal. And to get something out that has an amplitude of 3-4 kilometers or something like that, you really do need high signal to noise, high resolution data. So we're gonna have to go somewhere else to get that data, I think.
Remember too, with the rotation, those lines are awfully broad, so they're
Yeah.
very shallow.
Yeah, I mean, that's only a 2 km/s amplitude. The lines themselves are
250.
250 wide.
I just, yeah, so you did see the companion star, or this is a technique for seeing, I kind of missed that.
We haven't directly seen it.
Okay,
We've
okay.
shown that it's there, but it hasn't been directly used. That's one thing that we do want to do.
This technique, yeah,
Yeah.
gotcha. All right, let's thank Nick again.